And one of the IoT engineers picks up his smart shoe and calls another IoT engineer. And he asks, so, is this the Internet of Things? Have we built it? Have we achieved the full Internet of Things? And the other one goes, no, things will get much worse. So we are hearing that in the next 5 years, the amount of connected objects will drastically increase. All the way to 26 to 50 billion of connected objects, and that's excluding your regular mobile phones, your PCs, your laptops, just the smart devices that are being created right now. And we're also hearing that there are money to be made in this. Quite a lot of money. So what's so special about IoT that it will have such a drastic financial impact? Where are the money going to be generated from? And Forrester Research, IDC, and others have been trying to figure out where the long-term money will come from. And they suspect that they will be mostly generated by something that we call smart services. And the smart services is essentially a capability to analyze and predict what's going to happen by collecting the data from the connected devices and analyzing them. And there will be quite a lot of data by 2020. 44 zettabytes of data will be generated by the end of 2019. Out of these 44 zettabytes, 11 will be contributed by the Internet of Things. That's quite a lot. How do we visualize that? Well, if you take a iPhone 6, 128 gigabyte model, you backfill a wagon of iPhone 6, then this amount will be enough to circle the entire Earth. Well, of course, the data analytics discipline would go to hell if we were to store data in such fashion. But there are other problems. The amount of data that 26 billion connected objects will generate will be tremendous. The current situation is such that the data centers are sized to basically handle only comparatively small amounts of data coming from the connected devices. Mostly control traffic, mostly control level traffic. 26 million connected objects continuously, 26 billion connected objects continuously generating data streams would overwhelm our bandlinks in no time. But there are other challenges as well. Out of the existing only 4 zettabytes of currently stored data in the world, only 1.1% has ever been looked at. So why is that? One of the problems is that the structure of the information is not always apparent, or it can be simply lost. The data that we are trying to process is to a large extent unstructured, and and the problem of bringing together various sources of data and stitching them together is non-trivial. So there are efforts being launched right now, like the Eclipse Smart Objects Foundation. Another one is HyperCat, which are trying to standardize the format of the messages and the format of the data in the Internet of Things. These are notable ones, but it's long way to go. So, In the coming years, we will likely see yet another war of standards that will hit us. And until the dust settles, we'll have to live with the various non-standardized data formats. So even to be able to process the data, we have to remember how the data was structured. And that is not a simple thing to do, given the amount of various formats. So this is how we traditionally process data. We had our endpoints which were connected. They were sending the data to the data analytics backend, generating lots of data, and that was processed in our servers, deployed in either cloud or on premises or elsewhere. The problem with that is that it doesn't scale to such tremendous amounts of connected devices. What we are seeing right now is the rise of the new paradigm, where the processing becomes more and more decentralized, and the intelligence of the devices becomes higher and higher. So that means that in the data processing ecosystem, not only the backend servers will take part in processing the data and analyzing it, but also the endpoints themselves. And the architecture will ultimately look like this. We will try to avoid having all the data sent over to the data analytics backend, but rather the data will be pre-processed, throttled, stored in the endpoints, and only the aggregate summary will be sent to the backend systems for processing, for indexing, and for basically analytics. The backend systems that we will host will have to have some sort of control that will allow the endpoints to be contacted and reprogrammed, and the algorithms to be changed to adapt to the changing conditions, and also to reprocess the data which looks suspicious. Because one can argue that the big data is essentially about two things: looking for trends and looking for outliers. So the trends is in many cases when the data doesn't have dependencies across the devices, which is the case with most of the connected devices, the trends can be figured out at the device itself. And it is only when there are certain problems with that you have to actually look at the data and understand what's going on in the data center. So you're not essentially interested in all the data being delivered to the backend. So I work for an IT services company, and we had quite a few projects where we were looking for the systems or the frameworks or the open source software that would help us in building solutions that would be structured like this. The problem was that we couldn't find anything that would be readily available and that would be open source. And that's when we decided to build something of our own, which is now Project Ka. So Ka is an open source platform, which is the middleware for the IoT of things, Internet of Things. It's licensed under Apache 2.0 license, and it has quite a number of functions that are already available. So, as you can see here, there are 5 primary components to the solution. The central piece is the identity management. We also call it profiling. This is about understanding what your devices are, how they look like, what sort of software they are running, what sort of hardware, what are the users, and so on and so forth. By knowing the endpoints and knowing the population, you can start doing smart things about them. So there is the data collection piece. We also call it logging, which allows you to create the data structures and define what sort of information you want to collect from the field. The framework takes care of everything once you send the data to the SDK on the client. It transforms that into the byte stream, it sends that to the server, and it then sends it to the data processing system or the database. The other aspect is data distribution or configuration. This is where, in a single platform, you have the knobs to be adapted and adjusted in the client software. So this is something that you can use to fine-tune your data processing algorithms in the devices out there, and this is where you can reprogram them to as much extent as you need, to as much extent as your software in the clients is capable of. We also have messaging capabilities, which allows the devices to communicate to each other, and notifications system, which allows you to distribute structured events to the clients. Now, as you can see here, of course, there are higher level interfaces, such as the endpoint SDK API, and other server interfaces in the platform. In terms of transport, no devices are created equal. So we abstracted the transport layer so that you could use anything you like. Some people prefer HTTP. There are quite many of such. Others promote gaya or MQTT. We've seen people using SMS UDH messages. So it is essentially up to the architect of the application to decide what the transport layer will look like and how to use it. Finally, at top of this platform, you create the data analytics part and the application logic. And of course, some assembly is required in this part because this is what your product is about. Now, this is a very quick and very high-level introduction into the architecture of the platform. You can see several components here. The white ones are something that the platform supplies, and the yellow ones is something that either you or third parties supply. So there are control servers, which basically handle all of the control plane interactions, such as configuring your applications from the server, such as injecting notifications, collecting data, and so on. Control servers expose REST APIs and run user interface. Operation servers is where most of the heavy lifting is done, and they are designed to be horizontally scalable. They don't retain any data within themselves, so if an operation server fails, then the clients automatically and without any impact switch to another operation server. The bootstrap servers are, well, you can call them naming nodes. That's essentially where the clients figure out how to find the services of operation servers. The database layer is abstracted. We use several databases right now. I'm on which some SQL and non-SQL ones. The SQL part is easily replaceable. It's just a regular SQL interface. The non-SQL databases supported are MongoDB and Hadoop, and I'll talk about that a little bit later. Finally, the state of the server, the state of the deployment is controlled by Apache Zookeeper, so if a node fails, then the Zookeeper knows about it, and it promotes one of the backup nodes to the primary one. Finally, the clients is something that you build as the architects of the IoT products. And this is where you embed the client SDKs, which ship together with the Ka platform. Now that we know what the architecture is, let's return to the original problem. So we have clients which we want to make capable of processing. And we want to have a feedback loop that would involve the clients into the larger scale processing, which happens at the server backend. So you can see here several appenders. These are, well, we call them log appenders. These are for the data that is collected from the devices. You can see that the operations server maintains connectivity to the endpoints by supplying configuration information to the endpoints, and the endpoints in return send back the aggregate data. This is state 0. And the analytics system that you build yourself is it can be based on one of the data processing platforms. It can be built on its own separately. Keeps, well, you don't see that there, unfortunately, keeps connected to the gaya control server. And the control server sends back the updated configuration to the clients, making them reprocess or pre-process the data in a different fashion. Now, let me talk about one example scenario which we implemented based on this architecture. The solution is about processing, the connected software, which is incredibly open to a point when it is not even possible to create all of the test cases and run them in the lab. So essentially, it's open to any interactions, which is why we were seeing a lot of problems in the field that we were not able to capture in the lab, and we were not able to reproduce. So that created a problem. We had to know what's going well and what's not going well in the field, and troubleshoot these issues as soon as they appeared. Which is why we created this. And this will be a little bit geeky, but I'll try to go through this as quick as possible. The data collected from the endpoints was in the form of logs, and the logs were of two types. On the left, you can see logs which we call them aggregated logs. So whenever there were certain errors or exceptions in the client code, the client was filtering that data and creating a record in the internal database where it was counting the amount of abnormal errors or abnormal exceptions that it encountered. And it was supplying the summary of these exceptions on a daily basis to the backend processing system. The second part of the logs on the right is the data schema that we used for the detailed logs. And this one contained not only the summary, like here on the left you can see that the only information that we were sending from the endpoints to the data processing system was the log tag, log type, message that was captured from the clients, and the amount of recurrences of such error. The schema on the right enabled us to capture all the data, including the trace of the last several lines of logs from that thread which encountered an error. So let's see that the data processing system sees a sudden spike of a certain type of errors. So you can see that in the update manager is constantly seeing an IO exception saying that the request for a software update times out. So we could check that the software distribution is fine, right? We can download our software update from the update site. So we had to figure out what was going on wrong in the certain clients, and it would not really scale well if we were to enable all the detailed logs from all the clients. So what we did is we correlated the spikes coming from the clients with the client profiles. And the client profiles are the identities of the clients out there. So we were looking for the filter which would satisfy the minimum subgroup of the endpoints, which was seeing the unexplainable increase in the amount of errors. And we found something. There was an issue with that was based on Android, so the kernel version is 3.17, and the software build 2.03 was seeing certain problems. There was nothing else on other kernels, there was nothing else on the other clients. So that's why in Ka we could create an endpoint group which was limited to only the devices filtered corresponding to this filter. And that's when we used the the configuration subsystem. And in the configuration subsystem, this is a simplified schema of the configuration, which allowed you to enable extended logging for a certain type of error messages. So we were using the errors that we saw in the aggregate to enable detailed logging for these specific errors for the specific endpoints as specified by the filters. So Ka supplied the capability to distribute updates only to a selected subset of the endpoints on the right, which enabled extensive logging for that error in these clients. And this is when the data that they started to supply to the backend started changed. Basically, you see the left endpoint that keeps updating, keeps sending just aggregate data, while the rest of endpoints which receive the updated configuration were sending detailed logs, which allowed us to troubleshoot and understand where the problem was. So this is an example scenario of how we created a system that used distributed analytics, where the data was pre-processed in the clients in order to supply summaries of what was seen, and then enable detailed analytics by enabling specific logging features in the selected endpoints which were seeing problems. There are many more scenarios, and we would be happy to talk about these at our booth 44. You're welcome. And we are also showing a demo that some of you have already seen with these guys, which run based on the Ka installation, and they collectively search for an exit from a labyrinth. Thank you.
Thank you.
Questions?
Do you guys have any questions? I have a non-technical question.
Yeah.
From a general product perspective, are you distributing it this way because you get better performance, or if you do this middle layer middleware, I'm trying to understand, right? What do I really gain from this middleware where I could not before? It seems like you're able to better filter things. So maybe it's easier. I'm trying to understand.
Are you talking about distribution of the software as a middleware, or about distributing the intelligence and processing the data?
Both. In terms of, what you said in the beginning was, as you search for something that you can layer in between, you couldn't find something, therefore you created that layer, so to speak.
Right.
I'm trying to figure out from more of a business perspective, what am I getting? Is it better performance, faster processing from an endpoint?
Thank you. Understood. Well, essentially you need middleware in some form or another anyway, because you cannot have devices directly communicate to your database, for example, right? So you have to have a middleware layer that that essentially keeps track of your devices, that allows you to see what's going on, that allows you to collect data from them, and so on. What we are seeing is that many companies proceed with building this sort of software on their own, and essentially reinventing the wheel all the time, because this is like in old times when people were building HTML and HTTP servers for themselves, until they realized that this is not something that is business related, and then they can use something that is open source. So this middleware gives you immediately the functions that you would most probably need in building the connected software out of the box.
What vertical industries are your customers most heavily in?
Right now, well, this question actually has two answers to this. The first answer is where the customers currently are in, and that's mostly in healthcare, some manufacturing, so probably home automation. However, the platform was designed in a very vertical agnostic fashion. Basically, we don't restrict any data models to any specific industry. And that makes it configurable to the point where you can essentially apply it in any industry where you're building connected software.
Just curious who were the early adopters of the technology? That's right. Early healthcare? You don't have to name names.
It's personal healthcare. It's fitness tracking for personal healthcare.
Just curious, let's follow on to that. You talked about aggregating data at the edge before sending it to a backend analytics.
Yes.
What kind of compression or reduction did you see in the volumes for that specific use case that you talked about?
Yes, well, it was really, really dramatic. It was, I don't know exact numbers, but when we were collecting all the data that we needed for the data and for the analytics from the field trials, which were up to 100 devices large, the backend was pretty much overwhelmed. We used a Hadoop cluster of 16 nodes, and it took that cluster about 40 to 60 minutes daily to process the daily amount of information. Once we implemented this aggregation in the edge, we didn't even need Hadoop anymore. It was all fitting into just memory.
So did you say you used Edge only had 40 devices?
100.
100 devices.
Yes, for 100 it was taking quite a while for the Hadoop cluster at the backend to process all the data while we were transferring all the data in the trial. Because essentially, well, I can give more details about what that product was. It was actually a proxy sitting on Android and filtering all of the TCP and all of the UDP traffic. So what we were collecting were essentially IPDRs with huge amounts of information, source, destination, hashes of the content transfer, delays, things like this. So they were really huge. And in terms of just collecting logs, well, you can imagine how much it takes to collect all the logs from the client.
So what was the difference between, the Hadoop and the Ka version? You know, what made the difference? Is it the filtering mechanism?
It's this capability to enable pre-processing in the edge, in the clients. So the clients were preparing for us a summary of what we have seen over the last 24 hours, for example, right? And they were sending this data to us so that we were only looking for anomalies. Like I said, big data in many applications is a search for the trends and outliers, right? So the trend is probably not, you don't have to collect every single recurrence of an error to know how many errors happened during the day, right?
Did you lose any data by doing so?
We did lose, well, not all data is created equally valuable, right? So we did lose a lot of data which was not valuable to us.
Chosen for you. Thank you.
Okay, thank you.